Welcome everybody to the presentation of our CIDR paper with the title One Model to Rule Them All Towards Zero-Shot Learning for Databases. So in case you haven't watched TV over the holidays or have not attended any of the database conferences in the last 2 years, you might have neither seen The Lord of the Rings nor heard about Learn DBMS components. So let me quickly set the stage for what this paper is all about before I then hand over to my co-author Benjamin, who will guide you through the core nuggets of this work. First, let me introduce what Learn DBMS components are about, which is the main focus in our paper. In a nutshell, the main idea of Learn DBMS components is to replace a classical component, such as a database index, with a machine learning model. The question is now, what makes such a learned approach more attractive than classical handcrafted components? The main effect that makes such learned components in particular attractive is that learned components often provide better performance than classical components, since they can better capture complex effects such as data skew or data correlations. Moreover, at the same time, learned components can be automatically constructed by learning from observations, which significantly reduces the high manual engineering and tuning efforts that classical components such as indexes typically require. And the idea of learned components can not only be applied to replace database indexes, but as various papers have shown, learned components have been used already successfully for a wide spectrum of different DBMS components, including learned query optimizers and query schedulers, as well as many other DBMS components. So from a high-level perspective, learned components seem to be quite attractive. So what is the issue with learned components that we aim to tackle in this paper? To better understand this, let me illustrate how learned DBMS components are realized today. The predominant approach for realizing learned DBMS components is workload-driven learning, which we coin Learning 1.0 in the sequel. The main idea of workload-driven learning is to execute a representative set of SQL queries over a given database, and then use the observations to train an ML model which replaces the classical DBMS component. For example, that way a model for query cost estimation could be learned that can be used to predict the runtime for unseen queries, which is a core task of a query optimizer, for example. However, while workload-driven learning has shown promising results, there are several issues that render it unattractive in practice. A major issue is that for training a model, typically a huge number of training queries need to be executed on potentially large databases to collect the training data. For example, recent papers about learned query cost estimation have used training datasets with 10,000s of queries, which might take hours or even days to be executed. Furthermore, and even worse, the expensive training data collection is not a one-time effort, since it needs to be repeated if a new unseen database with a new set of tables should be supported, or even if data of a given database is updated, and thus the data characteristics change. With zero-shot learning, we thus propose a new learning paradigm to avoid the high and repeated cost of workload-driven learning. To avoid the high cost of workload-driven learning, the key idea of zero-shot learning is that we use a new approach based on pre-trained models that can generalize to unseen databases out of the box. For example, we could thus use a pre-trained cost model to enable learned cost estimation on an unseen database without the need to run any additional training queries. The main idea of how to enable such an approach is that we pre-train a zero-shot model across different databases such that it can learn how to generalize across databases. For example, for cost estimation, the model learns how expensive a query plan is given the data characteristics of a new database. Moreover, important is that pre-training is only a one-time effort. That means once a zero-shot model is pre-trained, it can be used for any unseen database without imposing any additional training overhead. To explain how this all works, let me now hand over to Benjamin.
To show the feasibility of zero-shot learning, we first look at physical cost estimation. So the task is to predict the runtime given a query plan, in this example, 300 milliseconds given the plan. And this is a crucial task because it's the foundation for picking the correct plans in query planning and also picking the right indexes or materialized views in design advisors. And today this is tackled using simple cost models, which are often inaccurate. And that's why we end up picking wrong plans in practice. And that's why recently it was proposed to use workload-driven learning also for learned cost estimation. But this comes with the downsides we discussed earlier. So you again need more than 10,000 training queries for an unseen database. So a natural question to ask is, can't we just train workload-driven models on multiple databases to achieve zero-shot models that then generalize to also unseen databases? Unfortunately, this is not possible because the workload-driven featurization is inconsistent for multiple databases. And this is not just some technical criticism. This, in fact, results in wrong predictions for unseen databases. Let me explain why the featurization is inconsistent. If we want to express that certain columns are queried in some query plan, we of course have to encode those columns. And the way this is done in workload-driven models today is with one-hot encoding. So for instance, in IMDb, the first column would be 0, 1, and then all zeros. Movie runtime column would be 0, 1, and then all zeros, etc. And then if we have a different database, let's say SSB, then the first column might be region, the second one might be price. And as you can see, they have identical encodings, but they have no similarities. The columns are different. They might not even have the same data type at all. And this is the main reason the featurization is inconsistent and the predictions will be off. And there is no simple fix for this problem. And the reason is that the assumption that the database is fixed is hard-coded into the model architecture. So models jointly learn the data distribution and also the system behavior, and that's why they can never generalize to unseen databases. That's why in our paper, we propose a zero-shot encoding with two main ingredients. First of all, the graph encoding. So the query for which we want to predict the runtime is encoded as a graph. And not only plan operators are encoded as graph nodes, but everything. Predicates, involved tables, involved columns, etc. are all graph nodes, which is a very flexible representation that can generalize. In addition, we also annotate the plan nodes with transferable features. That means that these features really generalize across databases, so they have the same semantics independent of the database. So for instance, to represent some attribute, we would use features such as the data type or the tuple width instead of one-hot encodings, for instance. In addition, we also provide data characteristics as features, and this is discussed in more depth in the paper. And then this transferable features, featurized representation is input for a graph neural network like architecture that then predicts the runtime. And of course, an interesting question is, does that work in practice? So here we compare with workload-driven learning. We vary the number of training queries for an unseen database, and we compare the runtime prediction accuracy. And as we can see, the workload-driven models need more than 50,000 queries. So this amounts to more than 60 hours of observed workload to match the performance of zero-shot models. And of course, a zero-shot model doesn't need any training queries at all for the unseen database. Of course, we could also use those observed queries to fine-tune a zero-shot model for a particular unseen database. As we can see, this even improves the performance further, and we obtain more accurate few-shot models. We believe that there are many more tasks beyond cost estimation that can be tackled using zero-shot learning. First of all, I mentioned it before, physical design tuning, tasks like materialized view selection. So we have some initial promising results here where we use zero-shot models to predict the benefit of materialized view candidates and then select the correct materialized views for a particular workload. In addition, there have been many results in the recent years in learned query optimization, but they all have the cold start problem. So you have to observe many queries on a particular database to come up with a good learned query optimizer. And we think this zero-shot paradigm could also help here. So in a really simple setup, we could just use our zero-shot cost model to enumerate plans and choose the cheapest plan with respect to our model. But we are sure there are more involved techniques also. There are also applications beyond databases. So we all know the data calculator paper by Stratos-Idreos, where the idea is to come up with new data structures by combining primitives and then obtaining an optimized data structure for a particular workload. But we think that navigating this space of primitives is quite hard. So picking the right primitives for an unseen workload will be very hard in practice. And we think that zero-shot learning can also help here because we have the flexibility to learn complex patterns, and we don't need executions for an unseen workload. In addition, we think there are also applications in machine learning systems. So there's one example where the placement of tensor operations was optimized for efficient training. So we basically want to assign tensor operations to GPUs in a distributed setup, which is a quite hard problem. And to stay in our terminology, this is workload driven. So for a particular architecture, we have to observe many placements to come up with the right placement. And we believe that zero-shot learning could make this much more attractive because we would not need to observe any placements for an unseen architecture in this case. So in general, we think that zero-shot learning could be a general paradigm for learned systems and make them much more attractive to be deployed in practice. So to wrap it up, zero-shot learning for databases is the idea to generalize to unseen databases without training queries at all, or only fine-tuning. So the few-shot case we've shown earlier. We think that this is interesting for cloud DBMS vendors, since the models work out of the box for new customers, because new customers will come with new data sets, with new schemas, etc. And our models will instantly generalize to those new customers. And we also believe that other zero-shot tasks could be supported in the future, such as physical design tuning, knob tuning, or even tasks beyond databases. With that, thanks for your attention, and now we are ready to take questions.